welcome back. We're going to talk about molecular biology today and some chemistry. And we're going to start out with some basic chemistry, and we're going to talk about the fact that the world, the universe, is made up of matter. And matter is anything that can take up space or has weight, or I should say, and has weight. So matter is anything that can take up space and has weight. There's three states to matter. We've got solid, a liquid matter, and then we have gas. Now matter and energy can be exchanged but cannot be destroyed. So you can turn matter into energy, and energy, like matter, cannot be destroyed. So we're going to talk about how we do that in the body. But energy is basically a definition for energy, especially when we're talking about chemistry, is the ability to do work. Now, one of the other things that you need to know is that matter, living or not living, is made up of what we would call elements. These are substances that cannot be broken down to simpler substances. All matter is made up of elements. So whether it's living matter or non-living matter, you have these elements. And elements would be things such as carbon, or hydrogen, or nitrogen, or oxygen, or phosphorus. These are different elements that we have in the world. Now, these elements can also be referred to as atoms. And so these atoms, such as carbon and hydrogen, we're going to be talking a lot about. And atoms are made up of what we would call subatomic particles. So for instance, if you were to look at an atom has what we'd refer to as a nucleus. And in the nucleus of an atom, we have what are called protons. And protons are positively charged. So these protons have a positive charge. Also found in the nucleus of an atom, or at least most atoms, are what we would call neutrons. And neutrons have no charge. So hence the name neutron, they are neutral. They don't have any charge. And these are the subatomic particles that are found in the nucleus of an atom. Now, floating around this atom in what we would refer to as an orbit, or we could call this a shell, or we could call this a valence. It just sort of depends on who you're talking to. But in this orbit, which is probably what we'll call it most of the time, are what we would call electrons. And electrons, they have a negative charge. And they circle around this nucleus kind of like a spaceship would circle around a planet. So in this overhead you can see this is the atom of helium, and here in the nucleus you have the protons, which are positively charged, and then you have the neutrons, and then you have the two electrons floating around in the orbit on the outside. Now, for something to be an atom, for us to be able to call something an atom, the number of protons must equal the number of electrons. So for instance, in this helium atom, notice that there are 2 protons and there are 2 electrons. So if you have 2 positive charges and you have 2 negative charges and you add those all together, then you would have no charge. You'd have a 0 charge. So we take these 2 protons and we take the 2 electrons, we add them together, and we find that also for something to be an atom, we can say that overall the charge is going to be neutral. So every atom, in order to be an atom, has to have an overall neutral charge. So if you look here, you have carbon. Let me write that over here. And when we write this carbon, you'll see that they write a 12 and and a 6 here. Now, carbon is what we would call the atomic symbol. Okay, so this tells us the C stands for carbon. The 12 is what we would call the mass of our atom, or the mass number. And then the 6 represents the atomic number. So, two terms I really want you to know. One is atomic mass, the other is atomic number. So, the atomic mass is where you take the number of protons and you add them to the number of neutrons, and then you get the atomic mass. So this gives you the atomic mass. The atomic number is going to be the number of protons in the nucleus. So if I tell you the atomic number is 6 and the atomic mass is 12, then how many neutrons does carbon have? Right, so carbon has 6 neutrons because we know it has 6 protons, and if the atomic mass number is 12, you just take 6 minus 12, that gives you the number of neutrons. Now, where we're going to find these symbols for each of the different elements is in the periodic table. So the periodic table, you can see here, has what are called periods, and the periods are going to be the horizontal rows, and then it also has groups, and the groups are the vertical rows. So in the horizontal or the vertical rows, doesn't matter, you can see the atomic number, and you can see on top. So hydrogen here, you can see the atomic number is 1, and the atomic symbol is an H, and then the atomic mass is 1.008. So you can find all this data on the periodic table of the elements. Now in humans, which is what this class is all about, we're really going to focus on 11 major essential elements. Now the 3 really big ones are carbon, oxygen, and hydrogen. Those are the ones that cause humans to be organic. If something is organic, now that's not the organic like at the supermarket, okay? This is chemistry organic. So to be organic, you have to have carbon, oxygen, and hydrogen. If you're organic at the supermarket, you're looking at something that was grown that doesn't have any pesticides or herbicides, or even nowadays any genetically modified organisms going on, okay? So that's a little bit different. Now, we also have not just the major elements, but we have what are called trace elements. And trace elements are where we have these atoms in the body in very teeny tiny amounts. So that's why we call them trace. Now, just because they're in teeny tiny amounts doesn't mean they're not important. So we have, for instance, sodium, potassium, calcium, iron. You've probably heard of all those. Super duper important in the body. But then we have a trace element, which the symbol for this is Se, and this stands for selenium. So Se is selenium. And you don't need very much selenium in your diet every day. You need maybe about 90 micrograms of selenium, and that's a very tiny amount of selenium. And you get this from eating plants. The plants suck it up out of the ground, and then when you eat the plant, you get the selenium. Now, if you don't have selenium, even in that really minute amount in the body, then what happens is your muscles all start to turn white, and then eventually they go into mush, and then you die. So just because something's called a major element or a trace element doesn't mean they aren't important. What that means is if it's a major element like carbon, oxygen, hydrogen, then what that tells you is we have a lot of it in the body. If it's a trace element like potassium, sodium, selenium, it means we only have a little bit of it in the body. But it is still very, very important in our body. Now, we've talked about atoms a little bit. We'll go into it a little bit more. But we can modify atoms. So an atom should have protons, neutrons, electrons. But we can modify atoms to become what are called isotopes. Now, isotopes, we're going to talk about this because they're actually very important in the medical field. And of course, that's what the majority of you are looking at going into, is in some type of medical profession. Now, isotopes are atoms with different numbers of neutrons, okay? And sometimes you'll hear people also refer to these as radioisotopes, because these are also atoms that have become radioactive. And when something is a radioisotope, it actually emits or gives off different types of energy. And so this energy can be harnessed and used in the hospital. So when we change the number of neutrons, now remember we started out with carbon, and I showed you carbon with the mass number of 12 and the atomic number of 6. But what if I showed you this? Now you have carbon with a mass number of 13 and an atomic number of 6. That tells you that there are still 6 protons, but now there are 7 neutrons. Or maybe you'll see something like this, carbon with a 14 and a 6. Now you know there are 8 neutrons, but there's still only 6 protons. What we've done is change the number of neutrons in order to have a radioisotope. And most of the time you'll hear people call this one just plain old carbon, because this is a carbon atom. This one they'll call carbon 13. This one they'll call carbon 14. Okay, and then this tells you it's a different type of atom. It's had neutrons added to it. Now, if you see here in the picture, you can see somebody's thyroid. And now the thyroid, we'll talk about this later, but the thyroid is a little tiny gland, kind of looks like a butterfly. The wings are on this side, it sort of goes across your trachea here. And the thyroid, many times, can become cancerous, or it can totally get out of control. So let's talk about this just a little bit, and then we'll talk about how we use these radioisotopes to help to get that thyroid back in control. So give me a second. Let me just erase all this. All right, now, if we're looking at the thyroid, okay, there's a really huge, gigantic connection in the body between the thyroid and the brain and the rest of the body, okay? Now, I don't expect you to memorize all this right now because we're going to go over it again later, but I want to kind of give you a little bit of an idea of why the thyroid is so important. so a bit complicated, but again, don't freak out because I don't want you to memorize all these hormones. We're just kind of talking a little bit about what the thyroid is and why we use radiation, but I want to give you some ideas here. So in the brain, in an area of the brain called the hypothalamus, which we'll see this later in a human brain, I'll show you that in lab. The hypothalamus makes a hormone, a chemical that can create a reaction in the body. So this is what a hormone is, okay? So let me write out the definition of a hormone for you. So, 3 parts to the definition of a hormone. So, a hormone is a chemical that is released into your bloodstream. And this chemical, this hormone, travels through the bloodstream and goes from point A to point B in the body. And then at point B, it creates a reaction, it creates a response. So thyrotropin releasing hormone is made in the brain. It's made in the hypothalamus. And it just travels a little teeny tiny area of the brain, gets into the blood, goes a little teeny tiny area below the hypothalamus to an area of the brain called the anterior pituitary gland. And TRH causes the anterior pituitary gland to release this hormone called TSH, or thyroid stimulating hormone. Now TSH travels through the blood and goes to the thyroid. So right here in the throat, kind of right below the Adam's apple. Okay? There's where your thyroid gland is located. Now, the thyroid gland makes 2 hormones. One is called T3 and one is called T4. And now here's where the big deal is. These hormones control metabolism. Okay? So now the question is, what the heck really is metabolism? So when I say the word metabolism, what do you think of? And most people, when I say metabolism, they think of things like, well, how fat are you, or how skinny is somebody, how well do you digest your food, and can you make a lot of energy from your food, or are you sort of tired and lazy all the time, you know, what is it that you feel, and how big are you as a person? But that's only part of metabolism. It's a little teeny tiny part of what our metabolism is. Because for humans, metabolism is every single chemical reaction that occurs in the body. That's metabolism. So how well can you grow your hair? How well do your fingernails grow? How well do you digest your food? How well do your kidneys work? How good is your heart working? Can you reproduce? Can you have a baby? These are all examples of part of our metabolism. But basically, our definition of metabolism is every chemical reaction in the body. And the thyroid controls the rate of metabolism. So how fast or how slow is your metabolism? So let's say that we have a person who there's something wrong with their thyroid. And now, because there's something wrong with their thyroid, they don't make enough T3 and T4. What's going to happen to the rate of their metabolism? It's going to go down, right? So now this person, because they don't have enough T3 and T4, both of these hormones are lower than normal, the rate of their metabolism is going to be lower than normal, and we call this hypothyroid or hypothyroidism. That's supposed to be a Y. So that is low metabolism or a low metabolic rate. And what if we have a person who has really high T3 and T4 production? What are we going to see for the rate of their metabolism? It's going to be super high, right? So now you're going to have somebody who has hyperthyroid or hyperthyroidism. So let's say that we have a person who has a low metabolism. They have hypothyroid. What do you think their weight is going to be like? Yeah, they're going to have a lot of extra weight on their body because they can't convert the food that they eat into energy. So that also means they're going to be super tired and super sluggish and they don't want to do anything. And can they think very well? No, they can't. In comparison to what if somebody has hyperthyroidism? They're going to be super energetic. They're going to be like bouncing all over the place like they're some kind of speeder or something. Can they sleep? Absolutely not. They're going to be up until 2, 3, 4 o'clock in the morning. They can't get any sleep. Usually they're going to be super duper skinny people because they go through their food energy so quickly. It eats up all of their muscles, so they don't have a lot of muscular strength. And this is a problem. Now, with hypothyroid, this one we can give the patient in pill form actually T3 and T4. And that will help them. It's not perfect, but it does help to raise their metabolism. But what about a person who has hyperthyroidism? They make too much T3 and T4. How do you take care of this? Well, here's where the radioisotopes come into play. What you're going to have to do is you're going to have to kill off their thyroid. And so what you're going to give this person is you're going to give them radioactive iodine. Okay? So iodine is part of both T3 and T4. To make up these hormones, you have to have iodine. And anytime we eat iodine, like for instance, you look at the salt that you eat, there's iodine in that salt. It's what we call iodized salt. So anytime we give iodine to a person, it goes straight to the thyroid. So what we're going to do for this person who has hyperthyroid is we're going to give them radioactive iodine. And that radioactive iodine will go directly to their thyroid and it will kill the thyroid. It releases tons. Remember, radioisotopes release energy. It releases tons of energy and it destroys their thyroid so they can no longer make any T3 or T4. And they drink this radioactive iodine to kill off the thyroid. Now, of course, what that does to your patient is it makes them instantaneously hypothyroid because they're not making any T3 and T4. So now they are going to have to take it in pill form for the rest of their lives. So this is one of the instances where we use radiation in the hospitals in order to cure certain diseases. And so, of course, there's a lot of other uses for radiation too. So, for instance, we use radiation to kill bacteria and to kill fungi. A lot of the food we eat, especially like fruits and vegetables, will go through radiation treatment. So it prevents the bacteria and all from destroying these fruits and vegetables. Of course, there's a lot of question about this because anytime you treat these fruits and vegetables with radiation, that also means that you're eating that radiation, because radiation doesn't go away, or it doesn't decay super fast. As a matter of fact, it usually takes a long time for it to go away. So does this radiation of our fruits and vegetables, does it affect us in the long run? That's really the question that we're wondering about. Any questions? Okay, so let's move on. And we're going to kind of hop back a little bit and talk about atoms again. So again, give me a second. Let me erase all this. Okay, so let's go back and remember, an atom has a nucleus, and in the nucleus is a positive proton, and then we also have a neutral neutron, and then going around the outside of this nucleus in an orbit is a negatively charged electron. Okay? So in this picture here, this is a hydrogen atom. And notice this is the atom that doesn't have any neutrons. All it has is one proton and one electron. And that's something that I want you to know about a hydrogen, is that a hydrogen atom has one proton and one electron. Okay? That's the only one I want you to memorize, but I do want you to memorize this because it's very, very important. And we'll talk about this more as we go along. Now, electrons, okay? Remember I said they move around in this orbit or a shell, or you can call it a valence. And there are actually, potentially, depending on which atom we're talking about, there could be multiple orbits, okay? So, in the first orbit, the one that's closest to the nucleus, this is the one we're going to call the first orbit. In this first orbit, there can only be a maximum of 2 electrons. That's it. So orbit number 1, we have 2 electrons. Now in orbit number 2, the maximum that we can have is 8 electrons. Now notice I put the electrons in pairs because they like to roam around in pairs together. So in orbit number 2, we have a maximum of 8 electrons. And so one of the things I told you, in order for something to be an atom, the number of protons must equal the number of electrons, so that overall atoms are neutral. Now there's one other really important thing that I want you to know about atoms, and that is that atoms like to be what we call stable. Okay? So let's talk about what does it mean to be stable. So look at this overhead here. This is a hydrogen atom. And again, remember I told you it has 1 proton, 1 electron. Here's carbon. We know carbon has 6 protons, and so therefore it must have 6 electrons. Now, both of these atoms are not stable. Both hydrogen and carbon are not stable. So, let's take this second orbit off for a second. And hydrogen only has 1 electron. That makes it very unstable. If, on the other hand, there were 2 electrons in this atom with its 1 orbit would become stable. So for this orbit, it has to be full of the maximum number of electrons it can carry, which is 2. That makes it a stable atom. if I put the second orbit here, and I add the maximum number of electrons it can carry, which is 8, it now becomes a stable atom. As long as there are 8 electrons in the outermost orbit, or the outermost shell, we have a stable atom. And this is what we call the octet rule. Okay? So whether it's the second orbit, the third orbit, the fourth orbit, doesn't matter. As long as there's 8 electrons in that orbit, we have a stable atom. So that's why hydrogen is not stable. It only has 1 electron in its one orbit. Carbon is not stable because look at its outermost orbit. It only has 4 electrons. It needs 8. So let's look at nitrogen here. Nitrogen has 1, 2, 3, 4, 5 electrons in its outermost orbit, so therefore it is not stable. Oxygen has 1, 2, 3, 4, 5, 6 electrons in its outermost orbit, and again that makes it not stable. Okay? Look at phosphorus and sulfur and tell me, are these atoms stable? Right. So phosphorus only has 1, 2, 3, 4, 5 electrons in its outermost orbit, so it's not stable. And sulfur has 1, 2, 3, 4, 5, 6 electrons in its outermost orbit, so it is not stable. So what's the big deal? Why do we care if atoms are stable or not stable? And let me just start off by telling you there are very few atoms that are naturally stable all by themselves. But atoms like to be stable. They prefer, they want to be stable. But if an atom is not stable, the good thing is that that means it's able to bond to another not stable atom. And when they bond together, it helps the two of them to become more stable. So atoms seek to become stable, and by doing that, they're able to bond to each other. If they're already stable, they're not able to bond to any other atoms, which could be a problem because if atoms can't bond to each other, we can't make what are called molecules. So we have 2 or more atoms that are bonding together to form these molecules. So it requires multiple atoms to bond together to form a cell phone, or multiple atoms to bond together to form a tree, okay, to form us. So we have to have this bonding or these molecules to form in order for us to be in existence or for us to be able to make things. So if every atom was stable, you wouldn't have any molecules. You just have single atoms floating around by themselves. So molecules usually form when 2 or more atoms bond together. Okay? So we're going to talk about different ways that atoms can bond together. And one of those ways is what we would call an ionic bond. Another is a covalent bond. And then a third that we'll talk about is a hydrogen bond, which is why I told you you need to memorize that a hydrogen atom is made up of 1 proton, 1 electron. Okay? So let's talk about first, when we talk about ionic bonds, what is an ion? Okay? So an ion is where we're going to take an atom and change it up a little bit so that with an ion, the number of protons does not equal the number of electrons. That's the big deal with ions. You actually have an unequal number of protons and electrons so that we can form this ionic bond. All right, so let me erase some of this stuff again, and we'll talk about ionic bonding and how this works. So first, a couple of terms for you. An anion and a cation. So an anion is going to be an ion that has a negative charge to it. A cation is going to be an ion that has a positive charge. Okay? So let's say that we have this atom here. Okay? So is this, well, let me just ask you this question first. How many electrons does this atom have? $11, right? So we have 11 electrons. Now I didn't write in the number of protons, but if this is an atom, tell me how many protons should this atom have? Right, it needs to have 11 protons, because for it to be an atom, the number of protons has to equal the number of electrons, so we have an overall zero charge. But then let me ask you this. Is this atom stable? No, it's not, is it? Because look, for an atom to be stable, remember we said that the outermost orbit has to have 8 electrons, right? So this one only has 1, so it's missing 1, 2, 3, 4, 5, 6, 7 electrons for this atom to be stable. Okay, so let's try another one. So, is this an atom? Well, how the heck would you know unless I told you that the number of protons equals the number of electrons, right? So, how many protons does this atom have? How are you going to figure that out? Just count the number of electrons, right? So, this atom has 2 plus 8 is 10. Plus 7, because it's missing 1 electron here. So this atom has 17 electrons, which also means it has to have 17 protons. And has to be overall neutral charge to be an atom. But are these atoms stable? And the answer to that has to be no, because we're missing 7 in the outermost orbit here, and we're missing 1 in the outermost orbit here. But if these two atoms got close enough together with each other, is there a way they could help each other out? Is there a way they could help each other become stable? Okay, absolutely. This atom could take this 1 electron and actually give it away to this guy. If it gave this 1 electron away over here, then this atom would become perfectly stable. It would have 8 in its outermost orbit. And if this atom gave away this one electron, this outer orbit here would disappear. There wouldn't be any electrons in it. And then the next one becomes the outermost orbit, and there's 8 electrons there. Could we, theoretically, possibly, kind of, sort of, could we take these 7 electrons and give it away to this guy and make them both stable? Yeah, we could, couldn't we? But it doesn't happen that way, because Mother Nature is seriously lazy, and we're going to do it the simplest way possible, which means we're going to take this one electron here, and we're going to give it away over here. Now, this atom has 8 electrons in its outermost orbit, and it has become perfectly stable. This one here loses this outermost orbit because there's no electrons there, so it doesn't exist anymore. And now it has 8 electrons in its outermost orbit, right? But now, okay, look at the difference though. Now this guy has 18 electrons, which means overall it has a -1 charge. And this one here now has 10 electrons, which overall means it has a +1 charge. So now this becomes a cation, this becomes an anion, and opposite charges attract. So these 2 ions will bond to each other. So if you look at the overhead for a second, that's what you see here. The first ion that we have here, this is sodium with its positive charge. This is a chloride ion with its negative charge. And so sodium here in this atom has given 1 electron away, and we end up with a positive charged sodium ion and a negatively charged chloride ion. So basically what you have is the positive charged sodium and the negative charged chloride bind together, and you get this molecule, which we call sodium chloride. Also known as salt. This is the stuff you sprinkle over your meal to get that salty flavor. But these are 2 ions, an anion and a cation, bonding together to form a molecule through ionic bonding. Any questions? No? We're good? All right, so now we're going to talk about covalent bonds. So take a look at this atom and tell me how many protons does this atom have? So there are 6 electrons and there are 6 protons. Yes? So this should have 6 protons here. We overall have a 0 charge. Now, is this atom stable? No, it's not, right? Because it's missing 4 electrons in its outermost orbit in order to make it stable. So what we're going to do is we're going to bond to this atom a hydrogen. We're going to bring in a hydrogen, which has 1 proton, as you know, and it also has 1 electron. Okay? And this electron, can it be given away to this atom in order to make this atom more stable? I mean, if we did, if we took this electron off of this hydrogen here, took the electron off and gave it to this atom here, which, by the way, this atom is carbon, it would help the carbon a little bit become more stable. Now it would only be missing 3 electrons. It would be closer to 8. But now here's the problem. If I take the electron off of hydrogen here, hydrogen does not become more stable. It becomes less stable. And we can't do that. That's just not something that's going to happen in nature. So with ionic bonds, we have giving away of electrons by one atom, and another atom receives that electron. So we make those cations and anions. With covalent bonding, we're not going to be able to give away and receive. Instead, we're going to share. Now sometimes you'll see with covalent bonding, sometimes electrons will be equally shared. And what I mean by that is electrons will spend just as much time around one atom as it will around the other. Or sometimes there will be unequal sharing of electrons. So in covalent bonds, if there is equal sharing, this is a nonpolar covalent bond. It's unequal sharing. This is called a polar covalent bond. So in this first one, we're going to talk about nonpolar covalent bonds. That means there's going to be equal sharing of the electrons. So again, this carbon is not stable. It only has 6 electrons in its outermost orbit. This hydrogen also is not stable. It's missing 1 electron in its outermost orbit. So when we talk about orbiting, that means this electron goes around the nucleus. It's constantly floating around the nucleus. But as soon as it gets close enough to this carbon, what the electron's going to do is it goes around its own nucleus and then jumps off and goes around the nucleus of the carbon and comes back again. Now electrons travel at the speed of light. They're traveling so quickly that hydrogen doesn't even miss the electron when it goes around carbon and comes back again. It didn't even know it was gone. It travels so fast. But if 1 electron is going to travel around this carbon, it's only fair that carbon does the same thing. So one of carbon's electrons, it'll travel around the carbon and then jump off and travel around the hydrogen and come back again. And this has formed what we call a covalent bond. Now, hydrogen basically now has 2 electrons. It becomes perfectly stable. Is carbon perfectly stable? No. It only has now 5 electrons in its outermost orbit. So let's try to help carbon out and make it more stable by bringing in another hydrogen. So if I bring in another hydrogen, 1 proton and 1 electron, this electron will go around the hydrogen orbit and then around the carbon, and it will come back again. And I'll do the same thing with this electron here. It will go around the carbon and go around the hydrogen and come back again. Now carbon has 6 electrons in its outermost orbit, and both of these hydrogens have 2. If I bring another hydrogen in here, 1 proton and 1 electron, this electron goes around my hydrogen, around the carbon, and back again. And I'll share an electron from the carbon with the hydrogen. And now this hydrogen has 2 electrons. This carbon has 7 electrons. And if I do it one more time, 1 proton, 1 electron, and I share electrons from hydrogen to carbon and from carbon to hydrogen. If you count in carbon, there are now 8 electrons in its outermost orbit, and each hydrogen has 2 electrons in their outermost orbit. These are all covalent bonds. They are all non-polar covalent bonds because there's equal sharing. I'll show you unequal sharing in a little bit, but these are all equal sharing. And now we have a stable molecule. Now you could draw this molecule like this, or we could do this. We could draw it like this. Each of these lines represents a single bond. That means hydrogen is sharing 1 electron with carbon, carbon is sharing 1 electron with hydrogen. So we could draw the molecule like this, or we could also draw the molecule like this, or we could draw it like this. Because that's what CH4 is, it's methane. Any questions? This is a really good time to write your questions down. Okay, so let's go on. Let's do another nonpolar covalent bond, just as an example. Let's kind of get this in your head a little bit. So this atom, again, has 6 protons, 6 electrons, overall 0 charge. This atom is carbon. It needs 4 electrons in its outermost orbit to fulfill the octet rule and to become stable. So right now, it's not. So then, let's talk about this one. Atom has 8 protons, 8 electrons, and it has an overall 0 charge, and this atom is oxygen. So oxygen is going to require 2 electrons in its outermost orbit to become stable. Carbon requires 4. So what we're going to be doing with this is we're going to be sharing electrons. Now, my question is, how many electrons can we share? Because carbon needs 4 electrons in its outermost orbit, but oxygen only needs 2. So you can only share the smallest amount. You can only share 2. You can't share all 4. Well, it'll help. Carbon will become a bit more stable. So what we're going to do here is we're going to take this electron from oxygen. It'll go around oxygen, hop off, go around carbon, come back. And carbon will do the same thing. It'll share its electron. And we're going to do it twice because oxygen can share 2. We'll share 2 electrons from oxygen to carbon and 2 electrons from carbon to oxygen. Now, oxygen is perfectly stable. It has 8 electrons in its outermost orbit. Carbon is not perfectly stable. So this molecule is not a stable molecule. And what that means is our first molecule, which is stable, cannot bond to anything else. This molecule, although a little bit better, a little bit more stable, it actually can bond to other molecules still. But this carbon has shared 2 electrons with oxygen, and oxygen has shared 2 electrons with carbon, so this is how we can draw this. This is what we would call a double bond. Or we could also draw it like this. Or we could draw it like this. This again is considered a non-polar covalent bond. So how would you know when we're looking at things in the human body whether it is polar or non-polar? Well, one of the good ways to know if something is non-polar is if carbon is involved. And a lot of times it'll be carbon and hydrogen, or carbon and oxygen, or carbon and oxygen and hydrogen. But if carbon is involved, we're looking at non-polar covalent bonding. So if this is non-polar covalent bonding, then we're looking at carbon being part of this molecule. All right, now we're going to talk about polar covalent bonding. And when we talk about polar covalent bonding, this is the unequal sharing of electrons. So we're going to have these 2 electrons share between atoms, but it's not going to be an equal sharing. It's going to be unequal, and I'll show you why. And the best example is probably this one, where we're going to use an oxygen. Remember, this has 8 protons, and therefore 8 electrons. So to be perfectly stable, it's missing 2 in its outermost orbit. So it doesn't fulfill the octet rule. Now, if we bring in 2 hydrogen atoms, remember we've got 1 proton and 1 electron. And again, there's no carbon going on here, so we can say, okay, this is not going to be non-polar covalent, this is going to be polar covalent. So hydrogen has 1 proton, 1 electron, overall 0 charge, but it is missing 1 electron in its outermost orbit to fulfill the octet rule. So what we're going to do is we're going to have 1 electron from oxygen, which is going to be going around the oxygen, and then eventually it will get off and go around the hydrogen. And then the same thing with hydrogen, we're going to take 1 of its electrons, it will get off and go around the oxygen. We're going to take 1 of the electrons from this hydrogen and do the same thing. We'll have it get off, go around the oxygen, and then have 1 electron from oxygen get off, go around the hydrogen. And now, is this a stable molecule? Well, let's see. Hydrogen has 2 electrons. It got 1 from oxygen. This hydrogen has 2 electrons now going around it. And oxygen has 1 electron from each of the hydrogens, so it has 2 extra. And so we've fulfilled the octet rule. And each of these atoms, as they do this sharing, forming these covalent bonds, become stable. So we have a stable molecule. Now we could also write this molecule like this, or we could write it like this, or we could write it like this. And so water has polar covalent bonds. So each of these bonds, these are single bonds, but these are also polar covalent bonds. Covalent, let's spell it right. Any questions about this? All right, so now my next question for you is, remember I said a little while ago that if a molecule is stable, that molecule is not able to bond to anything else, right? If the molecule is not stable, then it can bond to other things. Well, this is a very stable molecule. And anytime we have a molecule that's stable like that, that can't bond to anything else, this molecule is a gas. Which really sucks, because if water was a stable molecule and all it ever was a gas, that means that water molecules couldn't bond to more water molecules and you couldn't actually form a liquid. Because here's what happens. If you have molecules that are very stable, they float around all by themselves. And they float far apart from each other, and this is what forms a gas. Now, if we can get molecules to come together and start to bond together, we can cause that gas to become a liquid. And then if we can take those molecules and squish them really, really tight and pack them in on each other, we could form a solid, which is exactly how we form ice cubes. Is we take those water molecules and squish them together and harden them up and form ice. So if water is a stable molecule, that supposedly means that those gas molecules cannot come together and form water or form solid, which means I can't have ice cubes in my iced tea, and that, I don't like that. That would really suck. So there's got to be some way, obviously, no duh, for water molecules, even though they're stable, to be able to bond to each other. And nicely, that does happen. Now, notice, this oxygen is a much larger atom than hydrogen. So that when the electrons rotate around hydrogen, they don't spend nearly as much time going around this little planet as they do going around, let's say, this big planet. It takes way more time for the electrons to orbit this big planet. Which means that, remember, we started out with 8 protons, 8 electrons, we had an overall 0 charge. But now we have 8 electrons in the outermost orbit alone, with the 2 extra electrons in the inner orbit. So now we actually have more electrons than we do protons. So that even though the electrons don't stay on the oxygen, they'll travel back to the hydrogens. But even though they don't stay, they're there for most of the time. The majority of time, even the electrons from hydrogen are hanging out with oxygen. Oxygen is cooler, it's bigger, it's badder, it's better, so the electrons like to hang out there. So oxygen now has kind of, sort of, a negative charge to it. And so we write it like this. We say this is slightly negative. And the hydrogens its electron is hanging out at oxygen most of the time, so it's almost as if it doesn't have an electron. So now hydrogen is kind of sort of slightly positive charge. So we can do this slightly positive charge. So now let me rewrite it over here. We have an oxygen, and we have the hydrogens. And we know that the oxygen is slightly negative, and each of these hydrogens are slightly positive. This is what makes it polar. So it has like a North Pole, South Pole type of thing. And now if I bring in another water molecule with its slightly negative and slightly positives, look what happens. The negatives and positives will attract each other. And you have the oxygen bonding to the hydrogen with the negative and positive charges, and now you can start bonding water molecules together, and even though they're stable, because they're polar, they can bond together and they can form a liquid. Now watch. Remember, these are polar covalent bonds. Okay? But this bond here that I did with the dotted line, this bond is actually a hydrogen bond. Now, hydrogen bonds are what we would call weak bonds. Okay, now this is really, really important. So make sure you put this down in your notes, because we're going to talk about this a lot, especially when we get to proteins. So these hydrogen bonds are very weak bonds. And what that means is it doesn't take a lot of energy to break these bonds apart. And it actually doesn't take a lot of energy to form these bonds. So very little energy is needed to make the bond. Very little energy is needed to break the bond. Okay? So, doesn't take a lot of energy to make the bond or form the bond. Doesn't take a lot of energy to break the bond. The second really important thing is that these bonds can form very quickly, super fast, and they can also break super fast. So you can make the bond fast, you can break the bond fast. Okay? So that's really important, and it'll become more evident as we go along, as we're talking about proteins and why making and breaking bonds are super duper important. Now, one of the other things I want to talk to you about as far as this water is concerned, I'm going to give you a couple terms. And first, water is what we would refer to as a solvent. Okay? So a solvent is something that is able to break things apart. It helps to facilitate or to speed up. Facilitate means to help. It helps to speed up or to facilitate chemical reactions. Okay? So if I were to do something like this, let's say that I have, let's say this is a beaker, okay? And I'm going to pour water into my beaker. I'm going to fill this beaker up, and I'm filling it up with water. water is my solvent. Okay? Now, what I'm going to do is I'm going to add to this water a little bit of sugar. Okay, so I'm just going to make some sugar water. The sugar is the solute. Okay? So water is the solvent, sugar is the solute. When I stir it together and I make this sugar water, I have made a solution. Now typically, if you're not sure what's the solvent and what's the solute, maybe the solvent isn't water, maybe it's alcohol, maybe it's something else. Anytime something is the solvent, this is in the largest amount. So whatever in this solution is in the largest amount, this is our solvent. Anytime it's a solute, this is the smallest amount of something in our solution. Okay? So if you're not sure if it's a solvent or solute, whatever is in the largest amount is solvent, whatever is in the smallest is solute. And that helps to make up a solution. Okay, now one other thing about water. Water has what we call surface tension. So give me a second, let me erase some of this so we can talk about surface tension. Because surface tension becomes really, really important when we're talking about the respiratory system. So I don't know if this has ever happened to you, but let's say it's like summertime, it's a really hot day, and you're drinking a glass of iced tea and or soda, and on the outside of the glass, you know how sometimes it sort of sweats and everything. And have you ever taken this glass and like set it down on a glass tabletop and just left it there for a few minutes? And then after you set it down, you go to pick it back up and it's sort of stuck. It's like it's glued there a little bit. But if you slide it off, it'll come off. It's not like it's glued solid, not super glue or anything. Or maybe, have you ever had the experience where you've got two glass slides and somebody has put them away wet, and those two glass slides are stuck to each other, and you can't, pull them straight off. You have to sort of slide them apart. Well, that water that stuck your glass to the table or stuck those two glass slides together has created what we call surface tension. And tension sort of means like it's sticky on the surface. And water has a very high surface tension. So let me show you with like the glass slides, for instance. So let's say that this is a glass slide. And we're going to have it on top of another glass slide. Okay? And in between, we're going to put some water. Okay. Now, one of the things you can't see with the naked eye is the fact that glass is made out of a molecule that has a negative charge to it. So if you could look at glass, all sticking out of the glass are a bunch of negative charges. And now we take these water molecules and we drip some water in between our glass slides. And remember, our water molecules, all of the oxygens are slightly negative, and all of the hydrogens are slightly positive. Okay. Now, not only are these water molecules going to want to bond to each other, but they're also going to be bonding to the negative charges of the glass. So you'll have something like this, where a water molecule might bond to another water molecule, but you'll also have water molecules that are bonding with the positive hydrogens to the negative glass and forming these hydrogen bonds with each other. So what I want you to notice is that some of these water molecules were able to bond to the glass above, and some of these water molecules were able to bond to the glass below. So that your water molecules are grabbing the glass above and grabbing the glass below and sucking them together and holding those two slides together. Now these are hydrogen bonds, and remember, these don't need a lot of energy to make. They also don't need a lot of energy to break. So if you just slide the slides apart, okay, those hydrogen bonds will all break. No big deal. Okay, now this is what we call surface tension. Now look at this. Inside our lungs, we have these little grape-like structures, which are called alveoli. And we'll talk about this more when we get to the respiratory system. But very similar to glass slides, alveoli have a bunch of negative charges all around the wall. And when we inhale, we add water to the air that we are breathing. And you can tell when you exhale, you can feel that water. So the water ends up in these alveoli. And again, we have all of our oxygen with the negative charge and all of our hydrogens with the slightly positive charge, so that our hydrogens and our oxygens can bond to each other, but they can also bond to the wall of our alveoli. So notice these oxygen are bonding to each other. They're also bonding to the walls of the alveoli. And like with the glass slide, when the water grabs a hold of the walls of the alveoli, it pulls them in. It sucks the alveoli closed, and those alveoli, if they close and suck in like this, this is due to high surface tension, and we're going to die. So you do not want high surface tension inside your lungs. This is a big problem. This does happen with certain diseases, which we'll talk about, but typically in a healthy person, there is an oily coating that goes over all these negative charges and does not allow the water to bond. And that oily coating helps the water to kind of bead up inside the alveoli, and then you exhale that watery coating. And we don't have a problem in a healthy person with high surface tension in the alveoli. But again, when we get to the respiratory part, we'll go over what this high surface tension means. Any questions? Okay, just a couple more terms that I want you to know. And one of those terms is anabolic. The other is catabolic. So if I have chemical A plus chemical B, and I pour them into a beaker together and stir, and then chemical A and chemical B bond to each other, I have just had a reaction. This is some kind of chemical reaction. Or maybe opposite. I have chemical A, B, and I tear it apart into chemical A plus B. I pull those two apart. It's still a reaction, okay? But if I add the two together, I'm building something. This is an anabolic or a synthesis reaction. So anytime I build something, like in the body, I'm going to be weightlifting, so I'm building muscle. That is an anabolic, a building, a growing, or a synthesis reaction. If, on the other hand, I'm going to tear chemicals apart, and a lot of times we'll tear chemicals apart to produce energy for the body. If I'm going to tear a chemical apart, this is what we call a catabolic, or a decomposition reaction. Any questions? All right, so the very last part we're going to talk about on this video is we're going to discuss acids and bases. So let's do some definitions again of what is an acid and what is a base. So an acid, this is a substance that has hydrogen ions in it. Okay, so let's talk about hydrogen ions. Okay, so we talked about a hydrogen atom, right? So a hydrogen atom, whoops, let's throw that away. A hydrogen atom has one proton and one electron. Overall, 0 charge. But remember, an ion, okay, the number of protons do not equal the number of electrons. So now, what if I do this? What if I just take this electron away so that all I have is a proton left, and now I have a positive charge, a +1 charge, and I have a hydrogen ion. Doesn't look like much because all it is a proton, but that is a hydrogen ion. And sometimes you'll hear people call a hydrogen ion just a proton. So you could say acids are a solution that contains hydrogen ions, or you could say acids are a solution that contain protons. For example, again, let's say that I have this beaker. And what I'm going to do is I'm going to fill this beaker up with water. And then I'm going to put an acid into this beaker. Now this acid has hydrogen ions. Now the hydrogen ions cannot be bonded to anything. They have to be free, floating around in there to be considered an acid. Okay? Now what if I have this second beaker? So we'll say this is beaker A and this is beaker B. Okay? And I'm going to put hydrogen ions in this beaker. Which beaker, beaker A or beaker B, have the most hydrogen ions? Well, that's easy. It's beaker B, right? So if beaker B has the most hydrogen ions, it is also more acidic. So the greater the number, or we would also say the greater the concentration of hydrogen ions, the more acidic the solution. could also write it like this. These brackets, anytime you see brackets around this, it stands for concentration. So the higher the hydrogen ion concentration, the more acidic. Okay? Any questions about this? Okay? So then let's go on and let's talk about a base. Now, a base is basically anything that can bond to a hydrogen ion. Okay, this is the base. Anything that can bond to a hydrogen ion. So for example, here's a type of base, OH minus. This is a hydroxyl ion. Okay? And a hydroxyl ion can bond to a hydrogen ion, and look what we get. Water. Okay? Or how about this one? A hydroxyl ion can bond to sodium, and you will get NaOH. And by the way, since this isn't bonded to a hydrogen, this is still a base. NaOH is considered a base also. Okay? If it can bind to a hydrogen, it is a base. So just keep that in mind. Probably shouldn't have shown you the NaOH, but oh well. Just keep in mind, if it can bond to a hydrogen ion, that's what we're going to use as our definition of what is a base. So again, any questions? All right, so what about this? What if I have a beaker, and I'm going to fill this beaker with water, and again, we'll say this is beaker A, and then I'm going to take this beaker, fill it with water, and say beaker B, and then I'm going to put a base, a hydroxyl ion in here. Which one is more basic, beaker A or beaker B? Of course, it's going to be the beaker that has the most hydroxyl ions. That's going to be the most basic. So we have the same thing. The greater the concentration of hydroxyl ions, then the more basic the solution. Now remember, the brackets mean concentration. So the greater the concentration of hydroxyl ions, the more basic the solution. So I could also do this. Increase the concentration of hydroxyl ions, then you increase the base. It becomes more basic. Okay? So, some really smart scientists came up with this pH scale. So let's talk about the pH scale for a minute, and it tells us all about acids and bases. Now this pH scale goes from 0 to 14. Okay, so this is our pH scale. So of course 7 is about in the middle. So we'll do 1, 2, 3. Now the pH scale has everything to do with acids and bases. So what I want you to know is anything below a 7 is acidic. So if it's below 7, right below 7, it's acidic. Anything above 7 is basic. Okay, now, let's talk just for a minute because this is really, really important. Okay? Now, one of the things that I've noticed with people who typically take biologies and they want to stay in biologies, whether it's going into medicine or what it is, y'all hate chemistry. Okay? So everything we've been talking about today may be going thum, thum, thum over your head, and you're just not really enjoying yourself, and you can't wait till we get the heck out of this part. I totally get it. I completely understand. I'm the same way. But here's the problem. Our body is all about chemistry. That's what our body is. So you have to know this. You have to understand this. And some of it, you know, you may not use very much once you go into the medical field, but I'm going to tell you one thing you will use. And you will use this pretty much on a daily basis in the medical field. And that is the pH scale. Because when you're working in the medical field, you're not usually working with people who are healthy. You're working with people who are sick. They go into the hospitals, they come into the doctor's office, they're sick, okay? And many times when you're working with people in the hospitals, they're really sick, okay? And when we get sick, really sick, our pH changes. And that's a big problem. So you are going to have to work on a person who's really sick and help to get their pH back to normal. You've got to get them back to that homeostasis thing, okay? And what are you going to do if you don't even understand pH and you don't know what number is an acid and what number is a base? And I see this all the time. So by the time you're done with human biology and then you take anatomy and chemistry and you get back to me and we take physio together, I'm going to start talking about pH again. And you're going to go, oh man, I don't know what an acid or a base is. And I can ask students, okay, so a pH of 10, is that an acid or a base? A pH of 2, is that an acid or a base? And typically they go, oh, no. And you think, okay, all this time you didn't learn it. Okay, so here's what typically happens. You learn chemistry just long enough to take the exam, and then you friggin' dump the information. But at minimum, don't dump the pH scale. Get that stuck in your head. Pretend it's all about biology. Do whatever you have to do to get this sucker to stick. Because you need to know it when you work in the medical field as a doctor, a nurse, a dentist. I don't care what it is. You need to know this stuff. Respiratory, definitely, you've got to know this stuff. Okay? You have to know the pH scale. And you have to know anything below 7 is acidic. Anything above 7 is basic. And when we talk about acidic, remember again, we're talking about the concentration of hydrogen ions. When we're talking about basic, we're talking about the concentration of hydroxyl ions. So now look at this. The higher, now this is where people get confused, okay? So bear with me. The higher the concentration of hydrogen ions, the higher the concentration of hydrogen ions, the more acidic the solution. But watch, this is the big deal, the lower the pH. So look, a pH of 6 is acidic, but a pH of 3 is more acidic. It has more hydrogen ions. A pH of 4 is acidic, but a pH of 1 is more acidic. It has more hydrogen ions. Okay? So, as you go down the numbers here, down the scale, you have more and more hydrogen ions. so that a pH of 0 has the highest concentration of hydrogen ions on the scale. So, if you can do nothing else, then do this. The higher the concentration of hydrogen ions, the more acidic it is, the lower the pH. Memorize that sucker. Okay? On the other hand, look at this. We'll do it like this. The greater the concentration of hydroxyl ions, the more basic, the higher the pH. So, if you have a pH of 8 compared to a pH of 10, 10 is going to have more hydroxyl ions, higher concentration of hydroxyl ions, it is more basic. A pH of 13 is more basic than a pH of 10. A pH of 14 is the most basic, it has the highest concentration of hydroxyl ions. Any questions? Okay, now what about 7? So a pH of 7, this is what we call neutral. Because in a pH of 7, you have the same concentration of hydrogen ions as hydroxyl ions. So a pH of 7 is always pure water. 100%, nothing else, just pure water. So what if I gave you a beaker and it looked like there was nothing but water in that beaker, and I had you measure the pH of that beaker and the pH was, let's say, 10. Is that pure water? And the answer is no, it's not pure water. Something else has to be in it, because pure water has to be a pH of 7. I had a student who this a couple years ago, and she was all excited because you've heard, I'm sure, about people wanting to take alkaline water, and alkaline water is supposed to be so super good for you, and we'll talk about a little bit later why it's not. But she bought this alkaline water, and I don't know why she did this, because you could just go to the local grocery store and buy it, but she had alkaline water shipped from China, so I guess it was supposed to be something fancy, I don't know. And the alkaline water was supposed to be a pH of 10, which is pretty, oh, by the way, I'm talking alkaline, and I forgot to tell you this. Instead of using the word basic, we can use the word alkaline. It means the same thing, okay? So she buys this basic or alkaline water, which is a pH of around 10, which is very alkaline. So I told her, I said, well, you know, why don't you bring that in, and we'll measure the pH to make sure that, you know, it's exactly what you were supposed to get, what you bought. And so she did, and we measured the pH, and it was 7. So she was a little upset about this because she had purchased a gallon of this alkaline water, which was a pH of 7, which tells you it was just pure water, and she had paid $500 for this alkaline water from China, plus shipping. So probably not what she expected. Alright, so let's look at the overhead just for a second, and let's look at some of the differences in pH. So let's start at the bottom down here, and you can see a pH of 1 is what we call hydrochloric acid. That's some acid that we find inside of our stomach, and so that's usually a pH about 1 to 2. Lemon juice is a pH of 2. Tomatoes are about a pH of 4. And then we have coffee, pH of about 5. Saliva, urine, about 6. Now, human blood. This is the one I want you to memorize. All these other pHs of all this stuff I'm going through, don't memorize it. But I want you to know that blood has a pH of about 7.35 to 7.45. So the average is our blood pH is about 7.4. Okay, so this is for human blood. Alright, so I want you to have that memorized. Know that range, know the average. Baking soda, about a pH of 9, ammonia, 11, bleach, about a pH of 13, Drano, a pH of 14. Now, what would be worse for you? To swallow something that is a pH of 2, or to swallow something that is a pH of 13? Well, let's look. A pH of 2 is lemon juice. Typically we drink lemonade, so that doesn't really hurt us, but a pH of 13 would be like bleach. Not a really good idea, right? Not so hot to be drinking that kind of stuff. And so you would think acidic things would bother us a lot. But here's the weird thing. When the human body becomes acidic, and we become acidic every time we get sick. So when the human body becomes acidic, there's got to be ways to help us out, to change this. There's got to be ways to keep us from becoming too acidic. Because if we become too acidic, there's a lot of things in the body that are going to break down. And we'll talk about how that works later. But let's say that I drink lemonade. So it's summertime and it's really, really hot, and I decide I'm going to make some lemonade, which is about pH of 2, and I'm going to drink lemonade. Now, I'm not just going to drink a little bit of lemonade. I am going to pound that lemonade. Okay? Maybe I'll drink a gallon of lemonade. So keep that in mind. See this average of 7.4? Our body needs to stay in this 7.35 to 7.45. If it doesn't, we're in big trouble. So for instance, let's say that I have a patient who comes into the hospital and I measure the pH of their blood and it is 7.2. Typically, this is a patient who is extremely ill, close to dying. They're not good. And that's not much of a change in pH, 0.2. What if I measure a patient's blood and it is 6.8? This is just a change of 0.6. This is usually a cadaver. Somebody dead. They got a blood pH of 6.8. Not good. Or on the other hand, what if I have a patient who comes in and they have a pH of 7.6? Usually this is a patient close to death. 0.2 change. I have a person who comes in, they have a pH of 7.8. They usually are going to die very, very soon, if not already dead. So we can't handle very big changes in the human body. These little tiny changes make us extremely ill. Extremely ill. So now, what if I drink this lemonade? Remember, lemonade has a whole bunch of hydrogen ions in it. So I'm going to drink a gallon of lemonade all at one time. And that lemonade is going to go into my stomach, and from my stomach, all those hydrogen ions are going to get into my bloodstream. And what will happen when hydrogen ions in high concentration get into my blood? My blood will become more acidic. And if I pound a gallon of lemonade, there is potential that my blood could drop from 7.4 to 7.2. It could kill me. So I'm here to tell you lemonade is lethal. Of course, that's not true. You all know that. You can drink lemonade all you want. You're not going to die from it. And the question is, why the heck not? Why aren't you dying from lemonade? And that's because we have in our body something called buffers. These are very, very, very important chemicals. And buffers prevent our blood from becoming too acidic or too basic on a daily basis. So that if I do drink lemonade, because I have these chemical buffers floating around in my bloodstream, they will not allow the pH to drop. and it'll keep my pH at 7.4. So for instance, here's a buffer. Let me show you. Let's say I drink a ton of lemonade. That means I have a lot of hydrogen ions. And they're going to enter into my bloodstream. But already hanging out in my bloodstream all the time is a buffer. And this is the buffer. This buffer is called a bicarbonate ion. Now my kidneys make a lot of bicarbonate. My lungs make some bicarbonate. And so when I drink my lemonade with all the hydrogen ions, it's going to bond with my buffer. And I'm going to make this chemical, H2CO3. This is called carbonic acid. Now, carbonic acid is what we would call a weak acid. Now, what a weak acid is something that as soon as it forms, it breaks apart. So the minute it's there, it's gone. So carbonic acid will break apart into carbon dioxide and water. Now, remember, for something to be an acid, to change the pH, the hydrogen ion has to be all by itself. So if the hydrogen ion bonds with something like the bicarbonate ion, it's no longer an acid. It can't change the pH anymore. All it does is turns into carbon dioxide and water. So I pound a whole bunch of lemonade, and that lemonade bonds to my bicarbonate ion, and I just, I don't know, burp and pee, and I'm good, and my pH hasn't changed. But what if I have a patient who is on dialysis, and her kidneys are failing, and because her kidneys are failing, she doesn't make nearly enough buffer. She doesn't make nearly enough bicarbonate ion. Could potentially lemonade then be lethal for her? And the answer is yes. Because if she doesn't have enough bicarbonate ion in her system, all those hydrogen ions could drop the pH and she could die. And one of the things that you have to tell your patients who are on dialysis is they cannot eat or drink all those acidic substances anymore that they used to. It's a big problem for them. Alright, so the next thing that we're going to go over in our next lecture are looking at biomolecules, which are our carbohydrates and fats and proteins.